There, I think we can start already our live stream. Please let me know if you see something on your screen right now. Okay, I think you can already see something. Thank you, Josh. There. Okay, so I'm in real time board. You see some samples there? Okay, can I start? So I'm just gonna turn on I'm just gonna use my phone to read your comments. So I'm gonna go straight to what we're supposed to talk about in this live stream session. So again, I don't want you to treat this like a film showing, because this is not a film showing. So you've got to ready your notes, and later on we will be needing your calculator as well. I'll be asking you to participate in this. Okay, are you all ready? May I have some comments if you're ready with the things you need for the review? No comments yet? Are we ready for the review?
Ready na, madam.
Now, only Mr. Arcaliana answers me here. So, Paul, what's a G? Okay, Joshua, yes. Darren, ready. Okay, Paul. G means go. I think so. Okay, ready. So, we started our lesson with carbon hybridization, and we later on learned about determining the total number of sigma and pi bonds in your organic compound structure. So I want you to look at your screen for this one example just to help us recall. And then the rest, you go over the examination papers that I gave you last January. So looking at the screen, hi Trisha, looking at the screen, you have one compound here. So I hope you're looking at it. So you've got a compound, you have CH3 here, CH2O, CH2CH, then CH2. So you see this is an expanded structural formula of the organic compound, and our task is to identify the type of hybridization first for every carbon cluster in the entire compound. So every carbon cluster, if you recall, if carbon has 4 single bonds all throughout, that's an sp3. So in this case, where you see carbon with all 4 single bonds surrounding it, you'll get an sp3 type of hybridization. And if you look at your oxygen here, your oxygen has 2 single bonds, but remember, oxygen has 2 lone pairs as well. And the 2 lone pairs will signify another available orbital that will be used for hybridization later on. So in terms of other elements, not carbon, you have to count each lone pair that's present in that particular element. So in this case, O has 2 plus 2 other single bonds. That's a total of 4. So that means it will have an sp3 type of hybridization. So sp3 means 4 also, because you have 1 for S and 3 for the p orbitals. So 1 plus 3 is 4. So all sp3s means it has 4 available slots or available orbitals for bonding. Okay, I hope sp3 is clear to you. So everything that has 4 single bonds for carbon is sp3. And if there is a lone pair, you have to count it as another orbital that's available for bonding. Now, when we reduce these orbitals after sp3, we go to sp2. Now, if you look at the example here for sp2, you see that carbon is bonded 3 times. So you have 2 single bonds and 1 double bond. So in this case, if you see already a double bond, that reduces the number of times your carbon is bonded. So in this case, it's bonded 3 times. If it's 3 times, you only need 1 for S and 2 for P. So 1 for S and 2 for P, 3 in total. And so you get an sp2 type of hybridization. which is the same case with this carbon here, which is also sp2, because you have also 3 bonds. One of that is a double bond. So you see in this example, you only have sp3 and sp2 types of hybridization. Now, if you can guess it, if we have an sp, when can we get an sp type of hybridization? Can anybody tell me when can we get an sp type of hybridization? Like, what type of bond will you see in your carbon if it is sp? I will wait for an answer before I proceed. Brad, what's the relation of the poppy's face on your comment? I hope that puppy is learning. Okay, male. 2 double bonds? Why joke? If you have 2 double bonds, one on the left or one on the right or top or bottom, do you think male is correct? You get an sp if you have 2 double bonds. Anybody agrees to male? So sp means you only have 2 orbitals ready for bonding. So if you have 2 double bonds, that's 2 bonds, and male is correct. Brad, you just don't listen, okay? Please take notes of it. And if you can go through your previous notes, much better while I'm talking about these things. Not just to Brad, I'm talking to all of you right now. So while you're listening to me, please look at your notes because probably you forgot about this lesson already. So Ryan, welcome to the live stream. Okay, so sp, male is right. You can have 2 double bonds on your carbon atom, and another one is when you have a triple bond. When you have a triple bond, that means on the other side, carbon will just be capable of having a single bond. So in that case, you also have an sp type of hybridization. Okay, so far, are the types of hybridization clear to you? sp3, sp2, and then sp. There are only 3 types of hybridization for carbon. So sp3, sp2, and sp. If ever you forget about types of hybridization and you still recall the symbols sp3, sp2, sp, just remember that you just need to add the exponents of these sublevels. So s will always be 1, and whatever it is for p, you add it all in all, and the sum will signify how many times carbon will be bonded to. So sp3 is equal to 4, so 4 single bonds. sp2 is 3, so that means double bond, and then 2 single bonds, and then sp is just 2. Okay? So I hope I'm ready now to proceed to the sigma and pi bonds. So in connection with the type of hybridizations, we can also determine our sigma and pi bonds. Now recall what these bonds mean. Sigma bonds are the bonds that arise when you have head-on overlapping of the orbitals, your s and p orbitals. So when you have single bonds automatically qualify or automatically form sigma bonds. While pi bonds are present when you have the presence of your multiple bonds. When we say multiple bonds, it means you either have double or triple bond. So when you have sigma bonds, all single bonds are counted as sigma bonds. So if you get sp3, you can say that you don't have multiple bonds, you all have single bonds. So in sp3, the total number of sigma bonds you have is 4 because you've got 4 single bonds. So each carbon cluster here for sp3 will have a sigma type of bond. Now we will not include in the counting our oxygen for the moment. So we'll just have the carbon, focusing on the carbon. So all single bonds qualify to be counted as sigma bonds. Where when we reach our sp2 type of bonds, when we get sp2 and we see a double bond means 1 sigma and 1 pi bond. So when you have a double bond, always count 1 sigma and 1 pi for that. So when we look at this carbon cluster here, the one I'm pointing right now with the mouse, since you see 2 single bonds, so this is 2 sigma, and then 1 for the double bond, so that means a total of 3 sigma bonds, and of course 1 in the double bond qualifies to be a pi bond. So you get 1 pi bond and 3 sigma bonds in this cluster of carbon, which is the same with sp2, with this carbon here that I'm encircling. So you have sp2 here also. So you have a total of 3 sigma as well and 1 pi bond. If you get a triple bond, what do you have if you have a triple bond? How many sigma? So if you imagine a carbon with sp, and the sp is triple and single, how many? Let me just draw that now. So if you have something like this, see, triple bond and then 1 single bond, if you get this particular type of carbon cluster, how many sigma and how many pi do you have here? Can somebody tell me in the comment section, please? Correct, Miggy. So you get 2 sigma and, no, not 1 pi, Miggy. You're correct with the sigma, but it's going to be 2 pi. So it's going to be, thank you for the comments, you'll have, 2 sigma. So sigma can be represented with that symbol, and 2 pi bonds. Because a triple bond means you have 1 sigma only, and then the rest are counted as pi bonds. Okay? Will it still be the same if you have like this? What if your structure will be 2 double bonds? If you have 2 double bonds, what's the total number of sigma and what's the total number of pi in this case? If you have 2 double bonds in your carbon, how many do you think will you have? DJ, 1 sigma and 2 pi? Now remember, every time you get the double bond or a triple bond, one of that should be a sigma bond first. So it's going to become, if you are to change your sigma, DJ, how many sigma bonds will you get in here? Good, Jean. So you're correct. It's still 2 sigma and 2 pi bonds. So 2 sigma and 2 pi bonds. Also, if you have double. So that's the same, no, Miggy. It's a 2 sigma and 2 pi. Always remember, if you get a double or a triple bond, one of that is a sigma. Only one is a sigma. So since you have 2 double bonds here, 1 for every double bond is a sigma. So that's why you have a total of 2 sigma bonds. And of course, the rests are considered to be pi bonds.
Where is James Bond?
James Bond actually is in the movie, so he's not part of this. Mr. Alkane just asking some question, okay? That was a commercial break. So any questions about sigma and pi bond? So when you are counting for the total sigma and the total pi, it would be better that you just count the bonds that you see in your compound, remembering that all single and one of the double and triple bond is always a sigma bond, and the rest are counted as pi bonds. Okay? Can we proceed? I think it's okay now. We're ready to leave hybridization and sigma and pi bonding. That was it. And again, can you please go over the tests that we had about this for more examples? And if ever you got your answers wrong, please ask your classmates for those who got it right. Okay? Oh, how about oxygen, Gene? Oxygen, as what I've said, um, when you're identifying the type of hybridization for oxygen, you count your lone pairs as part of the bonding, or the part of the orbitals that's ready for bonding. So one pair is 1, so 2, and then 3, 4. So that's why it's sp3. But when you count for sigma and pi bonding, you don't count anymore your lone pairs. You just count the lines that you see. Okay? So oxygen here, if you count the total, can you count it for me right now? If you count the total sigma for this compound in your screen, how many do you think is the total here? I'm enlarging it right now. I'm zooming it out. Can you please count how many is your total sigma for this compound? Paul, can you count it? So you got here, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you get 15 sigma bonds. Gene, we're talking about the entire compound already. So we're getting the sum, 15, Cherry. I think it's 15. You don't count the arrows. Please do not be tricked by the arrows. So you get 15. I need your confirmation right now. So do you see 15 sigma bonds? Arancha, thank you for coming in. Welcome to the live stream. 15. Okay, DJ 15. So most of you got already the 15 sigma bonds. So can you count now the pi bonds? How many pi bonds do you see? How many pi bonds do you see? So you get, well, it's very obvious. You only count the pi bonds if you see multiple bonds. In this case, you're just seeing one multiple bond there. So how many? Male. Okay, just one. You're correct, male. So you get only one pi bond because there's just one multiple bond in your compound. So one pi bond. So total of 15 sigma and one pi bond in your compound. Okay. Any more questions before I proceed to the next topic? Thank you, Trisha, DJ, Paul, Miggy. Okay. How about the others? Okay. Can I have thumbs up or something that will signal me to go to the next topic? Yes, Miggy. One double bond. Yes, because of the double bond. So one sigma. Okay. So we proceed. The next one that we're going to talk about will be the nomenclature. So my technique here is for us to be fast because I've had some detailed explanation about the rules. What we can do is, if ever you forget the rules on nomenclature of alkanes, alkynes, and all the aromatic hydrocarbons, I want you to revisit again the videos that I made before, though the much detailed videos that explains all the rules, the IUPAC rules that govern the nomenclature. So what I will do now is just to refresh you, just to summarize everything that we had for the term, just to summarize everything by giving you some examples. So let's start with alkane. So when you get alkane nomenclature, you see that the primary thing we do with alkanes is you identify your parent. Your parent is the longest continuous chain of carbon atoms, longest continuous chain. And when you identify your parent, which is the longest continuous chain, the rest that do not belong to the parent becomes your branch. And when you name the branches, you name them alphabetically. and you have to number what carbon it is attached to in the parent. So in this case, for the first one that you see on your screen, you get a name as your parent because that's the longest carbon chains you have. So you get 9 carbons, and the rest that doesn't belong to your 9 carbons are automatically your branches. So because you have 2 branches here, you got a methyl in carbon number 3 and ethyl in carbon number 6. That means in the alphabet, E comes first before M. So you have to name ethyl first before methyl. So since ethyl is in carbon number 6, so you say 6-ethyl-3-methyl, and of course the name of your parent, which is nonane. It should end in ane because it's an alkane, and you've got no space there. So looking at the other examples here, so you get in this particular second example, the longest chain is this. So you get 8, and so the one that doesn't belong in your continuous chain is your branch. So obviously you got 1 branch here. So you got methyl in carbon number 3. So finally the name for this is 3-methyl octane. And to make it more complicated, if you see this particular structure here, to figure out the longest continuous chain, I hope you can figure this out. The longest continuous chain that you have is 10 carbons, so you get a decane here. And tracing the branches that you have 2 methyls, and one of that is a butyl. A butyl has 4 carbons, so you get 3,4 dimethyl, and butyl starts with B, so you've got to name the butyl first. So 5-butyl, 3,4 dimethyl, and then your parent decane. Okay. With regards to the counting, Paul, we start, yes, you're correct. You start numbering to where the branch is closest to, the nearest location of the branch. So that's how you start numbering. That's for alkenes, okay? That's for alkenes. And I hope you still memorize the equivalent alkyl name. Like for example, if you have 1 carbon, it means meth, so methyl. 2 carbons is ethyl. 3 meaning propyl. 4 means butyl. 5 is pentyl, and so on and so forth. So if you forgot those, please revisit your notes for those alkyl names. Okay? Thank you, Paul, for the question. And then the next one that you have is, of course, your longest here is having 8 carbons, and then you get an ethyl in carbon number 3, and you get ethyl for carbons 2 and 7. So you say 3-ethyl, 2,7-dimethyl. Now, why did ethyl come first before dimethyl? Because you don't count the D, for the alphabetization. You always go back to the first letter of your alkyl name. You exclude the prefix that will represent how many of that branch. Okay? What do you mean, what page in the book, DJ? I'm not sure what page, but it was in chapter 16. So go over in the first few pages of chapter 16 in the textbook. And I told you before, you copy that on your notes. So I think it's in your notebook as well. Okay. Any more questions? So I want you to go over the remaining 3 examples here on the on the screen, and I want you to figure out how come they're named that way. And I will be waiting for some of your queries, some questions about these 3 remaining examples. It's about alkanes. Okay, still about alkanes. You're welcome, DJ. I hope alkanes is clear now. Naming our alkanes is just easy because this is the basic of all the rules we've been learning in class. The rules will always be about the parent and then the branches. Then the parent has to be named where the branches are closest to. Oops, Paul, what is that comment? YouTube is alerting me that this could be a spam. What is that comment, Paul? Explain yourself. Cannot be read. Are these codes? What are these, Paul? Okay, so I think you've got no more questions for Alkane. Now let's go to alkenes. Okay, now alkenes and alkynes, they have more or less the same rule. And as what I have told you, your study guide are helpful tools for you. I hope you still remember study guide 1, which is on your screen right now. I hope you can see study guide number 1. Your study guide 1, if you recall, gives you all the details that you need to learn about alkenes, alkynes, and aromatic hydrocarbons. So basically, study guide number 1 will give you the summary of everything already. And this time, you place your answers in your notebooks. If you can recall, you place your answers in your notebooks. For those who forgot about the butyls, the normal butyl, the secondary butyl, the tertiary butyl, I hope that you can watch again the video because I'm not gonna tackle that up in this review. Okay, so the secondary, tertiary have to be learned on your own. And then I've already discussed that in one of the videos, how to name your unbranched alkenes. And this time the addition is you need to have a number where the double bond is located. So where the double bond is, you need to place a number. Remember, in the alkanes, we did not number the parent. But this time, in your alkenes and alkynes, your parent has to have the presence of your double and triple bonds. So that's why you have to indicate the location of your double or triple bond, except if it's ethene or propene, because they're very small type of alkene compounds. So they're very small, there are very few carbons. That means you don't have to number them because wherever you put the double bond, it doesn't change. It's just on the same place. So, but if you have more than 3 carbon onwards, then you have to number your double bond. So you got all of these examples and you have to draw that. And then the naming of the branch alkenes, always remember that if in the branch alkenes, you've got to choose the parent. The parent may not necessarily be the longest, but the parent should contain the double or the triple bond. Okay? And then the rest that doesn't belong to the parent of the alkene, that means you treat them as branches. And when you number the parent, you number it where the double bond is nearest to. So your basis, the first basis for numbering, it's not anymore the branch. The branch will be secondary, but the basis for numbering will always be starting from where the double bond or the triple bond is nearest to. Okay, I hope I made that clear. And then I have to let you recall how you answered your formative assessment number 5 and the drawing. All of them, all of these answers are found in your notebook, so please go over them. And then for the cis and trans alkenes, we've had a very detailed discussion about cis and trans and how we draw them. So I will task you to watch again the video about cis and trans alkenes because that's still part of the lessons of everything about organic compounds. So please recall, and just to give you an overview here, if you get a cis alkene means all the one attached to your carbon double bond are all on the same side. the groups attached to your carbon-carbon double bond are on the same side. So cis, same. While the trans are, the opposite groups. I mean, the groups are found on the opposite side of your carbon-carbon double bond. So that's how they look like. Please go over the video again, the lecture video, so you would recall how you should be able to draw them, whether you draw the skeletal or the condensed structure of your compound. Okay? So let me just go back to my real-time board. So these are examples of your alkene nomenclature. So in this case, you got in your first example, in our first example here, we got a straight 5-carbon chain with no branch. So that's a pentene. It should end in ene because it's an alkene. And then we number it, starting with this carbon, not from the right, but from the left, because that's where the double bond is nearest to. So the double bond is in between carbon 1 and carbon 2. So that means you choose the lower value number. So you got 1 pentene. Okay, 1 pentene. And then you get, in the second example, you have a hexene because your parent is this. Okay, this is your longest with a double bond. And so the one that doesn't belong to it is this. So that means you've got one branch here. And how do we number this? We number it beginning from the left again, because this will give you the lowest value for your carbon-carbon double bond. Because if we start on the right, you'll get carbon number 4 here, which is higher. So that means you opt to start from the left. And so numbering from the left, you'll get carbon 2 for your methyl. So 2-methyl-2-hexene. So still the same. If there's a number, you should separate the number from the name with a dash. Okay, and the last example for alkenes. So you got, of course, your longest here is this, obviously. And when you get this, your triple bond is here. And if you look closely, where should I number? From the left or from the right? Of course, it's obvious that we number from the left because that will give us the lower value. So you get 1, 2, 3, 4, 5, 6, 7, 8. And so carbon 7 has a branch. So you say 7-methyl and carbon number 3 is here. So that's where your triple bond is. And because it's a triple bond, your parent should end in YNE, ine. So that means that 7-methyl-3-octine. Not octene because it's triple bond. So alkene and alkynes have the same IUPAC rules for naming, and also the same rules when you draw it, vice versa. Okay? Any questions from the group before I proceed to our arenes? Any questions from the group? Are you still with me? I hope you are. Any questions? I guess there's none. So, madam, to clarify, start counting sa kung asa dool ang double bond. Yes, correct, DJ. Yes. Pero katong alkanes, the one with no double or triple bond, of course, branch is your basis. But this time that we have alkenes and alkynes, double or triple bond, they should be the priority when you number, not the branch anymore. Okay? I hope I answered you. Okay. Any questions, DJ? Any questions? Okay. Okay, so let's now go to our arenes. Arenes are your aromatic hydrocarbons. Oh, Arancha, madam, what if duha ka double bond? So, you will use the prefix diene. Diene, if tulo, triene. And in that case, when you have more than one double bond, you've got to number it such that the two numbers or the three numbers where your double bonds are should give the lowest sum, lowest total. So you've got to experiment on your structure, how you number them, so that you will generate the lowest sum. So if you have a cyclic structure, that's basically common in your cyclic structure. Like if you have cyclohexadiene. So if you have cyclohexadiene, or if you're looking at your arenes right now, di ba, arenes contain your benzene ring. And when we named our benzene ring, we named this as 1,3,5 cyclohexatriene. So when you have 1,3,5 cyclohexatriene, remember that can be your basis to recall the rules for cyclic structure. When you are to number your cyclic structure, if you have a double bond, that means you need to number it to generate the lowest sum of the location of your double bond. Okay? So, yeah, the priority is the double bond if you got double bond. So, if diene, Grace, if it's diene, asa mag-start, if you have to choose between the two double bonds where you have a branch, the other one doesn't have a branch, then you start where there is a branch. Arian. So you start where there is a branch. Okay? But if it's just between two double bonds, no branches, just make sure that the sum is the lowest possible value. The sum. So you look at the sum. But if there is a branch on one double bond, the other one doesn't, so you start naming, or you start numbering, I mean, where there is a branch. Okay? Thank you. Thank you for your questions. And you're welcome, of course. Okay. So let me now go to our arenes. So let me erase my benzene ring. So remember, our benzene is named as 1,3,5 cyclohexatriene. But I've told you to at least be familiar with the common names of some aromatic hydrocarbons containing your benzene ring. So the three actually are here on your screen. You've got your toluene, your phenol, which is familiar to you, your aniline. And then I think you've met benzoic acid before with your one of your exams. So you have benzene, and it's a carboxylic acid. So instead of naming them benzene and then carboxylic acid, you name that benzoic acid. And if you get an aldehyde in your benzene ring, you can just fuse the two names and you can say benzaldehyde. And if you get a CN, that's your nitrile, so you just name that benzonitrile. This is for familiarization, okay? And then I've mentioned before that there was an arrangement in your benzene that has 1, 2, 1, 3, and 1, 4. So in this case, if you've got orthosilene, ortho means you have 1, 2 dimethylbenzene. So silene is just a shortcut for your dimethylbenzene. That's a common name. But the ortho is, meaning of that is you have 1 and 2 where your dimethyl are attached to. And then if you got meta, if that's a meta, meta is 1, 3. So meta is 1, 3. If you get 1, 4 in your benzene, that's a para. That's a para, it will have a para prefix. So just be familiar again with these terms because you might meet them, and I hope that it will not be a strange word to you when you are trying to figure out the names of these structures. Okay? Well, styrene is another thing, but that can be skipped for now. And acetophenone, you may skip that for now. But the rest that I just discussed, please do recall them. Also the ortho, meta, and para. Okay? And then for arenes, I think that's the basic thing you need to remember for aromatic hydrocarbons. So in your study guide number 1, there was a tutorial on naming aromatic hydrocarbons. Please watch that again, just in case you forgot them. And then I let you answer these practice exercises in the book. Please go over the answers again. And if you wrote the answers on your textbook, much better. Go over, you can have a run through of all those items just to have more examples to help you recall about aromatic hydrocarbons. So please put a note. I mean, when you have a paper here and a pen, please put a note. Please put a note on your notebook that you need to study that. Just figure out where you are weak at, because the mo- the moment you're familiar with where you are weak at, then you can readily go through those items on your own. Okay, so I think it's time for us to proceed to organic reactions. Okay, now for organic reactions, on your screen you see the 5 organic reactions that we discussed. So there's substitution, elimination, addition, combustion, and condensation reactions. So all these 5, these are just the common organic reactions. There are so many organic reactions, but we'll just be taking up the 5 basic ones. Okay, so substitution, the word itself will tell you that it's substitution because you need to substitute something and for you to be able to take place the spot of an element. Elimination, on the other hand, is really completely eliminate and nothing substitutes the location of that element. So everything is eliminated, something goes out, and nothing replaces that. If something replaces that, then it becomes substitution. Third is addition. So addition is nothing goes out, but something's going to be added to it. So remember that addition and elimination are opposite reactions. So when you do the reverse of elimination, it becomes addition. And in addition again, you add, nothing gets out from the structure. And you got only one product. Combustion is the easiest you can remember because we assume that all combustion in this case is complete. So if you have complete combustion, that means you always have 2 products, carbon dioxide and water as water vapor gas. So carbon dioxide and water are 2 fixed products of your combustion reaction. And of course, the other reactant in your combustion reaction should be oxygen gas. Okay? And lastly, condensation. When we say condensation, that means that you produce water in the product. So you have to trace where water comes from. So water is H2O. You've got to trace how come water was formed in this reaction. So where did it come from? So you can trace what are the reactants responsible for the formation of your water. So let me just give a run through of the exam, because I think some of you did not get the correct answer for this in the exam. So in test 2, you have a box, then plus H2O, then you form your 2-hexanol. Hexanol is your alcohol, and 2 signifies where your OH is placed. So we said that addition is when you add something to your structure. So how can we predict? The answer to this is that you formed 2-hexanol and you added water. So when you added water and you see only OH, where did the other hydrogen go? So the thing that you can remember here is for the other hydrogen, so the other hydrogen is hiding here. For that other hydrogen to be added to your structure, there should be a multiple bond. In this case, that will be transformed to a single bond so that it can accept another hydrogen and OH on its structure. So when you predict these kinds of reactions, always remember that your parent will be always your parent. So hexanol means hex, 6. So your parent will never change. It's always the hex. But how do you manipulate your 6-carbon structure such that it will pave the way for the possibility of your addition reaction to take place? So that means if I will draw my hex structure 1, 2, 3, 4, 5, 6, and for OH and H to be added, that means I need to start with a double bond. Let me draw that properly. So that means I've got to have a double bond. Because if I have a double bond here, if you recall how I discussed this, the carbon in this end is a CH2. While if you have a single bond on the right side, that means you get CH3. So that means you've already accepted one hydrogen in that case. And your C, where the other double bond is connected to, this is a CH. That's a CH. But in this case, when you have on the right side, that just becomes your CH still. It's still your CH. That's where your hydrogen is hidden. So it doesn't change actually. It doesn't change, but you added OH. So for OH to be added, you're removing actually your double bond. So every time you're exposed to an addition type of reaction, that means you are converting your double, or it can be a triple bond, to make it all single bond so that it can accept additional elements, because in the first place this is an addition reaction. Okay, I hope you got that right. Comments from the audience that I have right now. So addition reaction is when you are converting or removing the presence of your double or triple bond to make it all single bond. Why the double bond is placed in the first carbon? Because if you look at the placement of your OH, that's where you put your double bond. Okay? And it always begins in the tip in this case. Okay? Question. Let me now proceed to number 2. Number 2 is what we've said, combustion, and it's the easiest. So combustion reaction, of course, you'll expect you've got an alkane and you added oxygen gas in the reactant side. So because this is complete combustion, the products that you will get are always your CO2 and your water. And because you are obliged to balance your equation, that means to balance this, because you have 4 here, that means you need to have 4 hydrogens on the right side, and that makes your O2 a total, that makes your oxygen a total of 4, because you have 2 here plus 2 here, so a total of 4. So that means you need to put a 2 beside O2 to make it all balance. Okay? So that's it for combustion reaction. Okay. Now it's time for us to go to elimination. As what we have said, elimination is the opposite of addition here. So if addition is the conversion or removal of your double bond to make it all single, so the reverse elimination is to make your single double bond. So this is already your product, your double bond. So it should come from being all single bonds, correct? So that means, of course, your parent won't change. It's still prop. So that means it's still prop, but all single bonds. But in this case, you are forming H2O. So what could be our attachment to propane to this so that you can form your water? And of course, if it's water, you always have OH and H. So that means you have to start with your, or you have to start with your 2-propanol. This is called your 2-propanol. 2-propanol because, again, your triple bonds location is here. And we said that the attachment to where your functional group will be is to the second carbon where your double bond or your triple bond is located. So we put it in carbon number 2. And then if you trace again our carbons here, this is a CH3 here, and this is a CH. If you go to the product side, this becomes CH2. So that means you remove one H, so one H from here, and this is still a CH. That means nothing gets removed but the OH. So OH here and one H from here will combine, forming your water. So that's how elimination takes place. Elimination takes place when you remove one H, in this case because water man ang na-eliminate. So you remove one H and the other one will come from OH. H and OH will always generate your water, H2O. So every time you eliminate water, you can predict it right by having always an alcohol or OH functional group in your reactants. Always. Okay. I hope that's clear. Now it's time for us to go to number 4. Condensation. So condensation is when you form water in your products. Condense. So like rain, precipitation, you form water. So condensation is you generate or produce water in one of your products. So let's trace this. So when you are tracing, you've got to analyze carefully where the elements are coming from. So in condensation, you've got ethanol. So you get ethanol and there's ethyl benzoate in your product and water. So at first, you'll look at OH here, which is, probably your H2O should come from OH and another H. So your problem now of tracing H2O is where does the other H come from? Because we're able to answer the OH from ethanol combining with an H that's still uncertain, we've got to look at the other product so we can trace where or how this come into the reaction. So ethyl benzoate, you've ethyl and you got ethanol. So that means the ethyl attachment of your benzene comes from your ethanol, the 2 carbons. So your 2 carbons here, your ethyl, comes from your ethanol. So that means whatever is left in your ethyl benzoate is one of your reactants in your condensation reaction. So that means we've got to draw only what's left, removing the ethyl because the ethyl comes from ethanol. So when we draw this, so this is our benzene ring for that. Sorry for my drawing. And then we copy still the C double bond O, O. But then we know that we lack one H to finally form your H2O, because the OH lacks one H to fully form your water. So that means this should have H there. That H will be the one to answer our question, how come water was able to form in this reaction? So this, let me highlight that, this H and this OH combine together to form your water, while the ethyl takes the place of H attached to O. That's why you form your ethyl benzoate. You see here? This is the spot where ethyl took the place of H. And that's where your ethyl got its location. So therefore, your reactant is, this is what we call your COOH, your carboxylic acid, which should end in oic acid, but it's benzene. So therefore, we name this as acid. So that's your reactant. That's your missing reactant. Okay. And of course, we're down to the last type of reaction here. We've got substitution reaction. So substitution reaction, you substitute something. And if you look at this particular reaction, trace whatever you're given. So you have 2Cl2 and 2HCl here. So that means because you're left with 2 chlorine in the products and you've got a total of 4 here, because you're going to write that as 2Cl2, right? So that's a total of 4 chlorines, but 2 bonded with 2 hydrogen to form 2HCl. So that means 2 chlorines substituted the spot for 2 hydrogens that went out of its way to bond with chlorine. So that means, if we can guess this right, that means the only thing we start this reaction is just your benzene. It's actually just your benzene, because you know that your C6H6, this every corner of benzene, this every corner, that means you've got to provide hydrogen for every carbon there, because it has 3 bonds each. In this case, the substitution takes place with your 2 hydrogens, particularly in carbon 1 and carbon 3. So that's why it's called meta-dichlorobenzene. Meta means 1, 3, and then 2 chlorine, so dichloro, and then benzene. So 2 hydrogen got out from benzene to bond with 2 chlorine, and the other 2 chlorines substituted to the 2 hydrogens that left out, and so you get meta-dichlorobenzene. Okay, so that concludes our organic reactions review. That concludes it. Okay, if you need to stop this and absorb, the things that I'm discussing, you may do so, and may encourage you to write this down again. If you have your paper with you, you can write this down again and try to answer it on your own and repeat it to yourself, whatever I just discussed about the mechanism of all these organic reactions. Okay, are you still there? I hope you're with me as I'm about to go to the next part of this review. Okay. Yeah, Jean. Let's pray for more enlightenment and strength. Yeah. Okay. On your screen right now, I'm posting again the poster, our guide for the guide for our functional groups. Now, I told you that functional groups will still be there, the 19 functional groups that you need to be familiar of. And when we speak about familiarization of these 19 functional groups, I hope that you can still recall how to differentiate one from the other. We're done with our anes, enes, ines, and then our aromatic hydrocarbons. But the rest that you see on your screen, alcohol, you're kind of familiar with alcohol, which is paired with phenol also. Then you get ether, we're always in between two alkyl groups. Then the epoxide, we said that you can leave that, you can skip that. Halo alkane is when you have just an alkane, but you attach a halogen as a branch. Then aldehyde is when you got a CHO, a C hydrogen, and then double bond O. And then the partner to aldehyde is a ketone where you remove the H and you get to replace it with another alkyl group. So you get a CO, C double bond O. And then another one that's related, somewhat related to that, is when you remove the H from aldehyde, but you replace it with OH, so you got C double bond OH, so COOH, so you get carboxylic acid. Please make sure that you know how to spell this, and of course you have to know how to pronounce it properly as well. So carboxylic acid, so you get COOH. And then acid anhydride, you got C double bond O with an O in the middle, so it's like a ketone, double ketone with an ether also. So ketone ether here. Then ester is the relative of your carboxylic acid, because you just remove the H and you still have C double bond O, and then R, you replace the H with another alkyl group. Amide is when you have NH2 or anything nitrogen, which is directly connected with C double bond O. And then acyl halide is when you have a halogen that's bonded with your C double bond O. And then the next one on the line is amine. So when you have amine, you got just NH2 paired with a purely straight chain alkanes, ordinary straight chain alkanes. Unlike amide, you have a C double bond O, but for amine, it's just the ordinary hydrocarbon chain. Nitrile is when you have your C triple bond N, or just CN when you get the condensed structure of it. Imine, I told you that you can skip imine for the moment. This is much more complicated. It's a continuation to nitrile. Isocyanate, you can also skip that, in the azo compound. And of course, when you have thiol, this is the only sulfur containing functional group. Sulfur and then hydrogen. Then arene, anything that has benzene ring, belongs to arene functional group. Male, is it still going to be identification for this topic, madam? Yes, it will still be. There will be parts wherein you will be naming the functional group. Okay? So not so different with what you had in our exams. So please go over our test 4.5, especially for those who didn't get most of the items correctly. So please go over that. And on your screen, it will be your task already how to name all of these functional groups. Take note of the ending, and sometimes you'll be given the common names, and the common names are more obvious than the IUPAC names. So those on your screen are the IUPAC name. Some of it might be done through common names, which is, again, I told you, it's going to be easier if it's common name because it's going to bear the functional group's names. You're welcome, Mel. Welcome. Okay. I hope that organic chem has been clear now to you. And we ended up organic chem with, again, the functional groups, the naming of them, and then the organic reactions. And basically, the introduction to organic chemistry, you just go over the details about the chemistry of carbon and what's so special about organic compounds, why are they different from inorganic compounds. So please go over where we started before. But those are little things. I'm just giving you the important ones, the most important one will give that will that will be helpful to you for tomorrow's exam. Okay, and then we went into equilibrium, which is our study guide number 3. So on your screen, I am showing you study guide number 3. I'm not showing study guide number 2 anymore because I believe that you don't really need much assistance of that, and you've got answers to study guide number 2, so please go over that. So this is our study guide number 3. If you recall, we let me zoom that out. We discuss about activation energy and the graph. So if you forgot about that, so please go over your textbook and go over the tutorial video about the graph. I won't discuss any graphing in this review, so please go over the graphs. I really forced you to draw the graph on your notebook, so please go over all the graphs that you have written on your notebook, which is for catalyst and its effect on activation energy. So you've got to draw the lowering of the activation energy when you are to draw reaction progress versus energy in your graph. And then determining your intermediate and catalyst in the reaction, there was a clear discussion about intermediate and catalyst in the reaction. So the basic idea for intermediate and catalyst is you need to know that you get the catalyst first. The catalyst is the one that is present in the reactant first step and in the product final step, because you need to retrieve your catalyst in the reaction because it doesn't participate. That's what we've said in the discussion. And then intermediates, after determining the catalyst, now you're ready to identify the intermediates. So the intermediates are the ones that are the compounds that are temporarily formed in the reaction. So if they're temporarily formed, that means you can cancel them if they're located on the left side and right side of your arrow in your chemical equation. So those that are temporarily formed. Okay, so make sure that you don't confuse the two. And as what I've said, get the catalyst first and then the intermediates after. And then you've got to copy the net equation by just copying whatever is left on the left side and whatever is left on the right side. Bearing in mind that your net equation has to be balanced also. And then we've got chemical equilibrium, concepts about it. And if you missed my demonstration there, so you can just go over the demo because that's going to give you more or less a lot of concepts about chemical equilibrium, just to help you recall that the rate doesn't change anymore if it's at equilibrium, but the concentrations does not change but not necessarily equal. It depends if it's product favored or reactant favored. And then we went to the calculations, which I will show you in a while. I'll give you the overview of the calculations for chemical equilibrium for problem solving. But I just want you to remember that before anything else, before you start any equilibrium calculations, first is you've got to check whether your equation is balanced. And once it's confirmed that it's balanced, then you are ready to check whether the amounts given are in molarity. If it's not in molarity, that means you need to make it molar unit. So molar unit, that's your mole. of solute divided by liters of solution. So please make it in molarity before you start it. And then you tabulate initial change and equilibrium concentrations, and then the calculations of the concentration values will be through getting the X. And the moment you get the X, you can get the equilibrium concentrations and eventually get the equilibrium constant. So you've solved this problem. Please go over your study guide 3. I'm pretty sure that's ready on your screen, on your device, because we've done that, we've completed that. So you can just access that wherever you are. Even if you're lying down, you can look at your solutions there. Okay, so let me give another example to illustrate the steps on solving equilibrium problems. On your screen right now, you see the reaction of H2 gas with fluorine gas, and this is a reversible reaction, forward and reverse, forming your two hydrogen fluoride gas. So in this reaction, it says that if the initial concentrations of hydrogen and fluorine gases are 1 molar and 2 molar respectively, determine the equilibrium concentrations of all the substances in the reaction if HF has an equilibrium amount of 0.06 molar, and then calculate for the equilibrium constant value. So first, check if the equation is balanced. Okay, 2H2F, 2 and 2. Equation is balanced, so that's okay. Second is, are the concentrations in molar? Yes, it's in big M, so means obviously I don't need to make it in molarity this time. So I can just proceed to the next step, which is I'm going to make a table. So let's make our table this time because the substances are here on top. So I can just make my initial here, then change, and then equilibrium. Okay, so I can make a line if I want to. So I make a line to separate that and this. And then I can separate I, then C, and then E. Sorry, I'm just using my finger right now, so I hope that table is still clear with you. Okay, so let me use another color so that the values will be clear. So let's plot whatever we are given. We're given the initial concentrations of hydrogen and fluorine, that's respectively. So 1.0 molar is for H2, and then 2.0 molar is for F2 gas. And then HF here has an equilibrium amount of 0.06 molar. So, as what I have said, you can't solve it if there's not at least one substance with two values given. And because HF is a product and no initial amount is given to it, we can safely assume that our product is empty, nothing at the onset of the reaction. So you've got no product at all. So in this case, we are now ready to fill up our change. So remember that to speed up the process of having the change, we've got to inspect our coefficients, and that's where we can get the X. The coefficients of H2 and F2 are just 1, so that means they're basically just X. But we said because they are reactants, they are consumed in the process, their amount should decrease. That means you've got to not forget to put the negative sign. Okay. While on the product side, you've got 2 as the coefficient, so that means that's going to be a 2x. And because it's a product, that means we're expecting the product has to increase during the progress of the reaction. That means it has to remain positive. So you've got positive 2x. So please don't forget the negative x, and then positive for the product side, and putting the coefficient value beside your x. And now we're ready to figure out the value of x. Because we know that the I and the E of HF, we can determine the difference of the two. So that means 0 and 0.06 is just equal to 0.06 molar. 0.06 molar is already equivalent to 2x. Don't ever change the 0.06. 0.06 is already equivalent to the 2x change. So therefore, if 2x is 0.06, how much is x then? X is therefore half of your 0.06. So your x in this case is negative 0.03 molar, which is the same on the other side. That's negative 0.03 molar. So now that our values are complete, we can already fill out our values for equilibrium for H2 and F2. That's 1 minus 0.03, then we get 0.97 molar. And on the other side, this is 2 minus 0.03 molar, we get 1.97 molar. So now that our values are complete, our equilibrium values are complete, that means we can already calculate for our K. So remember that when we write our K, when we write our Kc or Keq expression, you should not ignore your coefficient, and it's always products over reactants. So product in this case is HF, so that's HF squared over the reactants, multiply the concentration of the two reactants here, H2 times F2. In this case, they don't have an exponent because their coefficients are just 1. So now we're ready to substitute all their values. So you've got HF, which is 0.06 over, or squared, sorry, 0.06 squared over 0.97 times 1.97. Okay, so putting all of that in the calculator, you will get an answer of 1.88, 2 decimal places, times 10 to the negative 3. Okay, that is now your equilibrium constant value. Units are unnecessary, so you may not put unit for your KC. So that's it. Again, I want to encourage you to write this down again on your notebook, solve it on your own, then revisit if you got the correct answer or not. And then keep on doing it until you get it right. Okay, and then let me just sum this up. Let me just conclude this with the last part of our lesson on equilibrium, the Le Chatelier's principle, which I won't take up in this review, but please watch the 2 lectures about the effect of amount and temperature to the shifting of the equilibrium position in your chemical system, in your reacting system. So please watch that, and go look at your answers also in the textbook exercises about Le Chatelier's principle. Okay? So, yeah, that concludes everything for today. This concludes everything that we've tackled for this term. And that's basically the summary of everything. And just after tomorrow's exam, please don't forget to bring your scientific calculator. Remove the cover, please, when you start taking the exam. No need to bring periodic table, just your calculator. I will allow you to use pencil, provided that your final answer has to be written using the permanent ink. That's all I am asking from you. And please have presence of mind, and please organize whatever thoughts you have right now. It can be overwhelming to have so many topics, but it's going to be fine. You've gone through this. Just relax and clear out whatever fears or worries you have. You can do it. Okay? So that concludes this. If ever you want to watch this again, it will just be, you can just access it in Narcademy channel in YouTube. Okay? So yeah. So let me end this with my famous quote: "Don't stop learning, relearning, and unlearning." Till next time, looking forward to more lecture videos with you. Bye!